So, first of all, good morning to everyone. We are sorry for the delay. We had some problem of connections this morning. We did several trials in the last days, but you see, Murphy's law is the strongest law in the physics of universe. So, before starting, I would like to spend some words, some comments about the content of these lectures, what these lectures will be about. Well, the aim of this course is to give you a self-contained short introduction to the analytic theory of Frobenius manifolds. Of course, in these periods, it is already a privilege I can do these lectures at the Blackboard. I am very grateful to the mathematical physics group of the University of Lisbon for asking me to give these lectures and to giving me the possibility to do on live on YouTube. Despite the fact that in this room there are just two people, the audience from the web can still ask questions via comments. These questions will be read by a person in the room, and I will answer probably towards the half of the lecture of today, when I will plan to give a pause for 5 minutes. Okay, I'd say we can start. So, the first topic I want to discuss are Frobenius algebras. And let's start with some conventions. So, in this lecture, I will consider a field K of characteristic 0. So you can choose, if you just to fix ideas, you can fix K equal Q, R, C, the one you prefer. And another convention is the following. In this course, we will always consider algebras over the field K which are commutative, associative, and unital. Okay, having said, let me introduce one of the main objects of the lecture of today. What is a Frobenius algebra? A Frobenius algebra structure on a space, first of all, okay, so let's consider a finite dimensional algebra over K a Frobenius algebra structure on V is defined by the datum of a symmetric bilinear non-degenerate form that I will denote in the whole course by eta, such that it is compatible with the product of the algebra in the following sense. Eta of A times B, comma C equals eta of A, comma B times C, where A, B, and C are elements, arbitrary elements of the Frobenius algebra. I will call eta the Frobenius metric or Frobenius pairing. So, a Frobenius algebra is this. We have a finite dimensional algebra over a fixed field of characteristic 0, and such a algebra is equipped with a symmetric bilinear non-degenerate form eta, which satisfies such a remarkable compatibility property with a product. But let me give you another way, another equivalent definition of a Frobenius algebra. So a Frobenius algebra structure on B can be equivalently defined by the datum of a linear form theta, which is in the dual of V, such that the pairing eta defined by the following formula, eta of A and B is defined as theta of a product, well, such that such a pairing is non-degenerate. So I claim that, given a Frobenius algebra according to this definition is the same that to define to give a linear form theta with the following property. Well, the proof is very simple. If we are given a Frobenius algebra in this sense, we can easily reconstruct theta just by pairing an arbitrary element with a unit of the algebra. So, in this direction, just define theta of A to be eta of A, comma 1. The opposite, by the way, is you can easily, it is just a simple check that this compatibility condition by a pairing defined as follows is satisfied. It's just a check. Okay, I want to start to send you a message. The main message I want to send you is that Frobenius algebras are ubiquitous in mathematics. And I will start now to give a series of examples, and I will take these examples from a very different part of mathematics, which apparently are very far from each other. But of course, the first example one should always give is the trivial example. So I will start with example 0, which is the trivial one. So the trivial example of Frobenius algebra is the following. Just take V equal to the field K and fix an arbitrary lambda in K different from 0. And set theta to be the linear form defined by multiplication by lambda. This is trivially a Frobenius algebra over K. More generally, any finite field extension of K is equipped with a Frobenius algebra structure and in particular we can take as theta any non-zero linear map. So any non-zero linear map theta works. So an arbitrary linear map from V to K works since being a field extension, but it's a morphism of field. So we always have that the kernel of theta is 0. Let me do indeed a remark. This condition indeed is equivalent to say, the condition on theta is equivalent to say that the kernel of theta does not contain any non-zero ideal. Okay, but let's move on and let's consider another example, example 1, coming from measure theory. So let me consider a finite set omega equipped with a positive measure and set V to be the set of all functions from omega to R. So this example will be a Frobenius algebra over the real numbers. And set theta of f to be just the measure of this function. Well, it is easy to see that this defines a Frobenius algebra structure over R. But of course, this example is, as you can see, is still a bit elementary because I am considering a finite set. I am considering a finite set because in this course I will mainly focus on finite dimensional algebras. But this is not necessary. The infinite dimensional theory of Frobenius manifolds is very rich, and let me, for example, give you an interesting example of infinite dimensional Frobenius algebra arising from measure theory. So by relaxing the finiteness condition of a dimension, consider the space of all continuous functions on the interval 0, 1. Again, this is an infinite dimensional algebra over the real number, and set theta to be just the Lebesgue integral of a function f. It is an easy exercise of real analysis to show this property. I leave to you as an exercise. It is very elementary. So this defines an infinite dimensional Frobenius algebra. Okay, the following example I want to discuss comes from representation theory. Well, first of all, it's better maybe to keep the definition, and let me erase here. I start to erase here. So this is example 2. Let me consider a finite abelian group G say, let's enumerate the element G, and G0 assumed to be the unit of G. So let's consider the group algebra with coefficients over K of G. So elements of this algebra are formal sums of this form, where the coefficients alpha I are elements of K and Gi are elements of G, and the operations are defined as follows. The sum is the sum of two such a series is given, obviously, as follows, and the product as well is defined Gi, Gj as follows. So there is, of course, an obvious way to look at these formal sums. There is another natural identifications of elements of this group algebra with, so natural identification with functions f from G to K. So V is naturally isomorphic to functions, K-valued functions over the group G, And according to this identification, the multiplication here defined is just a convolution of two functions. We are taking f and g, their product evaluated at h, maybe it's better to call h the function and g the element of a group, is defined as follows: f of alpha h alpha 1 g. Of course, here I am considering and I am using the integral notation for later purposes. Here I am using the measure which counts. It's just another way to write this. Okay, up to now we have an algebra over K, and I want to define a Frobenius algebra structure over this V, and I can define such a Frobenius algebra structure by defining a linear form theta. And such a theta is defined as follows. So theta from V to C will be defined by sending an arbitrary formal sum to the coefficient of a unit. The corresponding eta indeed is non-degenerate. Assume indeed to have an element u such that this is 0 for any element of a group algebra of G. Then U will be of the following form, and in particular, we can consider the pairing with the inverse of an element Gi. And this is clearly equal to alpha I. So as you can see, if we assume that U is such that the pairing with an arbitrary element of V is always 0, then all the coefficients of U are 0. Here it is alpha. So this shows that U indeed is 0, and consequently eta is non-degenerate. Well, actually, we can even generalize this example to the case of a non-abelian group. If G is not abelian, take V to be the center of a group algebra. So such a center clearly admits a structure of K vector space, and it is closed under the product here defined, and consequently it has a K algebra structure, and the same theta defines a Frobenius algebra structure. And moreover, let me also do a remark. In terms of this natural identification, now such a center, in such a case, such a center can be naturally identified with the space of a so-called class functions of G. That is to say, all the functions f from G to K such that they are constant on conjugacy classes. That is, F evaluated at G is equals F evaluated at H times G times H inverse for an arbitrary element GH in the group G. So this is another example of Frobenius algebra which comes from representation theory. The example now I want to give is a different example. It is a Frobenius algebra structure on a space of polynomials. I give it because I want to later to generalize this example in two different directions. So, example 3 is the following. So, fix a natural number in n star and let V to be the quotient of a polynomial ring in one indeterminate t modulo t to the power n. The claim is the following. Any linear form theta from B to K such that theta of Tn minus 1 is non-zero defines a Frobenius algebra structure. How to prove that? So, again, what we need to prove is the following, is that the pairing eta is defined as follows, is non-degenerate. So assume there exists an element A such that theta of A times P equals 0 for any P in this quotient. Well, A, the most general form that A can have is the following. We will have a power of T times another polynomial with non-zero constant term. Let me call this C0 plus C1 times T plus up to order n minus 1. So we will have minus 1 t n minus 1. So I claim that h must be greater or equal to n. And in such a quotient, automatically, this means that A is 0. How to prove this? Well, let's call this polynomial phi of t. Phi of t is a polynomial. We can look at it as a polynomial over. We can just deal with it as a polynomial, not an element of a quotient, and we can consider the following. We can consider the following element. So take 1 over phi of t. We can consider formally the Taylor expansion of this function. So take so the Taylor expansion at t equal to 0 of the function 1 over phi of t. I am assuming that C0 is non-zero. And let's call such a Taylor expansion, I don't know, phi tilde of t. And of course, this is an infinite series, but we can truncate this series at order n. So truncate at order n. And it is easy to see that this defines indeed the inverse of the polynomial phi inside V. So I will denote again by phi tilde the class in this quotient. If h is strictly smaller so if h is strictly smaller than n, then I can take p to be equals to phi tilde of t times t to the power n minus 1 minus h. I plug in here. By assumption, I am assuming that this is 0, but the linear form was supposed to be non-zero on t n minus 1. Okay, so which is absolute. So we have a very concrete Frobenius algebra over the space of polynomials. I will use now this example to, this example will be generalized in two different directions. The first direction comes from topology, and this is from algebraic topology. Example 4. Example 4. So let M be a compact manifold of even dimension. Orientable of dimension 2D. So for example, you can take a smooth projective varieties over complex numbers. A complex, for example, a complex projective variety. And define V to be the direct sum of all cohomology group of M in even degree. And we will consider complex numbers now. Well, I want to show that this direct sum is, well, first of all, it is naturally a kept of an algebra structure, and actually it is a Frobenius algebra structure. So cohomology, classical cohomology gives us an example of Frobenius algebra. What is the product and what is the form theta? The form theta, by the way, I will refer often to the form theta as the Frobenius form. So we have eta, which is the Frobenius pairing, and theta, which is the Frobenius form. So the product is the cup product. In cohomology, we have a naturally defined product which can be introduced as follows. Well, we have an obviously natural map from M to the product of M with itself, which is called the diagonal. It just sends an element to the pair. So x goes to x comma x. Whenever we have a morphism of topological spaces, we have morphisms in cohomology, but in the other way around. So such a morphism induces morphisms in cohomology. So we have a morphism from the cohomology of M times M to the cohomology. Of course, here now I am using just the even part. To the cohomology of M. And by Kuehne's theorem, the cohomology of a product is just the tensor product of the cohomologies. So what we have is a bilinear map. It is a bilinear map on the even part of cohomology. And we can interpret such a bilinear map as a product. This is the cup product. This defines the cup product. And it will be denoted by the union symbol. It is a cup symbol. If you want to, of course, there is a simpler realization of this product in terms of differential forms. We could realize cohomology as cohomology rings of differential forms, the RAM cohomology. And in such a realization, so if we use the RAM cohomology, then the cup product coincides. The cup product coincides with the wedge product of differential form. Okay, we have a product which keeps with an algebra structure. Let's define theta. What is theta? Theta is just the pairing. So the Frobenius form theta is just the pairing with the fundamental class of N. So, in other words, theta of A, we have a duality pairing between cohomology and homology, and what we are considering is the homology class given by the space itself, M, And we are considering the pairing of the cohomology class A with a fundamental class M. Again, in terms of the RAM cohomology, such a pairing is realized by integration over M. It is just theta of a differential form alpha is equal to the integral of alpha over M. So we should prove the non-degeneracy of this product, but this is the Poincaré duality. The claim of non-degeneracy of a Frobenius metric eta is the content of Poincaré duality. We have a perfect pairing alpha, beta, if we realize cohomology as different cohomology of the RAM cohomology. Poincaré duality asserts that such a pairing is non-degenerate. And indeed, we can recover our example 3 by specifying a choice of a particular M. We can, indeed, you can recover this example 3, can be recovered by taking M to be the complex projective space of dimension n-1. So this is exactly the classical cohomology algebra of a projective space Pn-1. And as linear form, here as I said, here any arbitrary linear form with such a property defines a Frobenius algebra structure. Here I specified a geometrically interesting form, the integration over M. Okay, but I want also generalize example 3 in a different direction. The example 4, and the following one will be somehow the germ of two classes of examples of Frobenius manifolds that will be described in the next lecture. So we have in example 5, let F1, Fm be elements of a ring of formal power series in M indeterminates, and let's assume that they are without constant term. Assume that the quotient V, so let's take the quotient and assume that it is of finite dimension. Well, one can show that the Jacobian determinant has a non-zero image in V, and generates there a one-dimensional ideal. Exactly as before, one can prove that an arbitrary linear map theta from V to K defines a Frobenius algebra structure if and only if the ideal I is not contained in the kernel of theta. So let's try to understand in which sense this example generalized the previous one. Well, in the previous one, instead of a power series ring, I had a polynomial ring in a single indeterminate. I had a single polynomial, so I had a single f, and I considered the quotient, the ideal. So this derivative is just before I was taking quotient modulo Tn. Before I was so this determinant is n times Tn minus 1, and so now here the ideal I in the previous example is the ideal generated by Tn minus 1. So in the previous example. So the corresponding bilinear form of course, as I said, so here I claim that I can take an arbitrary map. However, we will, with such a property, an arbitrary map whose kernel does not contain this ideal I. However, we will fix a choice for theta. In particular, I will consider the following. Okay. Well, at least over complex numbers. In the case k equals c. I will consider the following integral. So 1 over 2 pi I to the power m times the integral of the function g of z, dz1, dzm over f1 fm of z, and the integral is done over a complex sphere that is the locus of points of Cm, such that the modulus of Fi equals rho for all I from 1 to n, and rho is a positive number sufficiently small. Well, it is a theorem of Grothendieck that the pairing, the Frobenius pairing, the pairing induced by such a choice for theta is indeed non-degenerate. And so it defines a Frobenius algebra structure. Before doing a pause, I would like to finish this first part of the lecture by doing some comments on these last two examples. The example coming from topology and this example of quotients in the series of formal power series. Both examples are so-called Gorenstein rings, example of Gorenstein rings. Now, I don't want to give you precise definitions of what it is. Let's see. Well, just, okay, definition I can give. This is example 6. So, we have a ring, A, which is commutative, Artinian. I will explain what it is, and assume to be local. So we have a local ring, so by local we are assuming that A has a unique maximal ideal Artinian means that it satisfies the descending chain condition that is, if we have a descending chain of ideals, well, the Artinian property claims that whenever we have a descending chain of ideals, such a chain must stabilize at some point. Definition, we define the circle of A to be the annihilator of a maximal ideal M, that is, the elements of A such that A times M equals 0. A second definition is to be Gorenstein. A is Gorenstein if the following two equivalent conditions are satisfied. The circle of A is, does not contain any non-zero ideal, so is a simple A module, and equivalently, since we are assuming the ring to be local, this is equivalent to say that the circle of A is isomorphic to the quotient of A modulo the maximal ideal. This definition was given by Grothendieck, who was inspired by a work of Gorenstein, and according to the tradition, Gorenstein himself was fond of claiming that he actually didn't understand very well the definition given by Grothendieck. I claim that the two examples I gave before are examples of Gorenstein rings. And we have a theorem, remarkable theorem. If A is a commutative local algebra over K, finite dimensional, then the following are equivalent. A is Frobenius. A has a unique minimal ideal. A minimal ideal, what it is? It is an ideal which is minimal in the poset of ideals with respect to inclusions. So it means that there is no non-zero ideals between 0 and the ideal itself. And 3, A is Gorenstein. So in the local case, Frobenius algebras and Gorenstein rings are the same thing. In particular, for example, in cohomology, what is the maximal ideal in cohomology? Are differential forms, all cohomological classes which are not in H0. So 1 forms, 2 forms, 3 forms, till to the top degree. By the way, in 1963, a paper appeared with a title on the ubiquity of Gorenstein rings. So, by Bass, Heman Bass. It is a very famous paper for people working in commutative algebra. So, I hope with this series of examples to have sufficiently justified the claim that Frobenius algebras are ubiquitous in mathematics. We had examples coming from representation theory, measure theory, topology, and I think that now it could be a good point to stop for a pause, 5 minutes. Okay, welcome back. And first of all, a person in the audience here in the room, well, we are just in three, not so many people, but let me notice a mistake I wrote before. In the example coming from algebraic topology, I wrote something wrong, something like H even equals of M times M equals H even tensor H even. Clearly this is false because in general we also have a contribution due to the odd parts. The point is the following, is that I want to avoid the odd degrees, cohomological classes in odd degrees. I could develop a theory also by allowing odd degrees, but this would lead us to a notion of Frobenius superalgebra, in which we also have a superstructure. And I don't want to develop such a theory, simply because we don't have the time to do that. So in that case, what one should do, you define the cup product on the cohomology, so on all possible cohomological degrees, and then you just take the even part of cohomology. Okay? So thank you very much for the remark. Okay, now I want to discuss another source of Frobenius algebras coming from physics. Unluckily, we don't have the time to explain the history of physics, and since the course is mainly intended to be addressed to mathematicians, I will follow an axiomatic approach. So now I want to discuss Frobenius manifold, Frobenius algebras, and two-dimensional topological field theories. So what is a two-dimensional topological field theory? I will follow Attia in what follows. And in what follows, I will denote by sigma a compact smooth manifold orientable and oriented with boundary the sigma. So an orientation on sigma induced an orientation on the boundary the sigma. But in what follows, I will not assume the sigma to be equipped with the orientation induced by the one on sigma. So, by the way, we also have, okay, actually not a manifold but a surface, sorry, I restricted just to the two-dimensional case, surface. And in such a case, the boundary is a one-dimensional manifold, compact and without boundary. So we have a classification theorem for one-dimensional compact manifold without boundary. And we set, in particular, it says that the sigma is a disjoint union of cycles of S1. So I will set C1 to be the disjoint union of oriented cycles. As I said, not necessarily, the orientation is not necessarily the same induced by sigma. Not necessarily the induced orientation. So, a two-dimensional topological field theory is an assignment the pair sigma, the sigma, both equipped with orientations of a vector space which will depend on the pair, we will denote this in this way, assumed to be finite dimensional over, well, let's fix once for all over complex numbers, and also a vector inside such a vector space. Such an assignment is assumed to depend only on the topology of a pair sigma and the sigma. In particular, we can consider a distinguished pair. We have, let's fix delta to be the closed disk, unit disk in C, and S1 to be its boundary. And in particular, to the pair delta and its boundary, we will have an attached finite dimensional vector space, and I will denote by A this vector space. Okay, I have to impose some requirements on this assignment. So the linear space A sigma de sigma is defined as follows. A of sigma de sigma is defined to be C if the sigma is empty, that is, if sigma is without boundary. Otherwise, we have a product, a tensor product of k vector spaces where k is the same k of a disjoint union of cycles. And in particular, I have to explain who is AI. AI is equal to A, the one associated to the disk, if the orientation of Ci is coherent with the one induced by sigma. Otherwise, we take its dual. Okay, moreover, we require the following three axioms. The first axiom is an axiom of normalization. We can consider the following pair, sigma de sigma. So we take as sigma the cylinder. When I draw these pictures, I always mean the outward, I mean the convention of keeping the surface with the orientation defined by an outward vector from the surface. So, for example, we are taking this orientation, and such an orientation on sigma induces an orientation on the boundary. But here, so in particular, the induced orientation would be the following: tuck and tuck. But here, actually, in this axiom, I consider a cylinder with these orientations for the boundary. Well, the axiom is the following: this pair is associated with, well, we have A star times tensor A, because one of the two is not coherent with the orientation induced by the cylinder. And I have to define what is the vector. Well, I require, this is just the identity of A. A second axiom is the axiom of multiplicativity. Assume you have a disjoint union of pair. So you have one pair which is a disjoint union of two. To each of these I can associate a vector space and a vector. Then I require that the vector space attached to the disjoint union equals the tensor product of the two vector spaces, and also the vector. I assume that the vector associated with the disjoint union is a decomposable tensor equals to the tensor product of the two vectors attached to the two surfaces. And finally, we also have an axiom of factorization. So assume you are given two pairs which are equal outside a ball. Equal outside a ball. And inside the ball, they have a following form. So one of them is as follows. This is sigma and the sigma with some orientation. And the other one is this one cutted here along a cycle. So I have this and this is sigma, sigma prime, and this sigma prime. And here, the two boundaries are equipped with these orientations. Let me call Cj0 this cycle and Cj1 this cycle. So we have a natural map. So the vector space attached to this pair, according to the definition, will have two spaces more in the tensor product. But we can contract. We can use a contraction map. So we have a natural J0 J0, J1 contraction map. From A sigma prime, the sigma prime, to A sigma, the sigma. And such a contraction map is the obvious one. You take, here we will have, here J0 and J1 stands for the position in the tensor product. So here I will have A1, tensor blah blah blah, tensor AJ0, tensor blah blah blah, tensor AJ1, tensor ta ta ta. And here I have two copies less. I have A1, and we can, and as you can see, I put the orientation in such a way that that this one is not coherent with the one induced by the surface. So actually these two are not the same vector space, but are one the dual of the other, so I can contract these tensors. The axioms is the following. We require that the vector attached to the pair sigma de sigma is the J0, J1 contraction of a vector attached to the pair sigma 1 de sigma 1. Okay, this is a definition. I gave an assignment. It depends only on the topology of a pair. I defined how it is defined. So I explained how it is defined for arbitrary pairs, and I imposed three axioms: normalization, multiplicativity, and factorization. Okay, now I claim that behind all that there is a Frobenius algebra structure. Indeed, we have the following theorem. A theorem that for many years it was just a folklore, but it was rigorously proved by Abrams, Quinn, and other people. Theorem the space A, that I recall you is the space attached to this pair, carries a natural structure of Frobenius algebra. I have to explain what is the product, how it is defined, and what is the Frobenius form. So the product is defined as follows. I can consider this surface and the boundary equipped with the following orientations. A two topological field theory attached to this object, to this pair, a vector space which is A star times A star times A. Because two of the cycles of the boundary have an orientation which is not the induced one by the surface. And moreover, we also have a vector inside this. So what is this? Well, this is just the space of morphisms from A tensor A to A. In particular, we also have a vector. Such a vector, C, defines a product on A. So this defines the product. But we need to define the Frobenius algebra structure. So what is the Frobenius form? The Frobenius form is the vector attached to such a pair. We are taking just hemisphere with boundary with opposite orientation with respect to the induced one by the surface. So we have A star as a vector space attached to this, and theta inside A star defines the Frobenius pairing, the Frobenius form. So, how to prove this theorem? Well, we need to prove commutativity, associativity, and non-degeneracy of the induced metric. So, commutativity. It follows from the following obvious remark. I can consider this surface, this pair, but this pair is clearly equivalent, diffeomorphic to this pair. So here I have so here, as you see, I attach these tubes that to which, according to the normalization action, we just have identity attached to these pieces. And this proves commutativity. So this corresponds to the entries of a product, right? We need to prove associativity of a product. Associativity. Associativity follows, again, from a picture. And here we attach another pair of pants. So this pair here is identity, multiplication, multiplication. So this is, what is that? This is just this. Here A, here B, and here C. This is diffeomorphic to again the same orientations. And this is A times B times C. So we have a commutative associative algebra. I claim there is a unit. I leave to you to prove that the unit is this hemisphere with this orientation. And we also have a metric. Recall the metric eta A and B is defined as follows. You need to consider theta of A times B. But we know what is the product, we know what is theta. we just put together everything. So we needed to glue the pair of puns, which is the multiplication, with the Frobenius form, which is this hemisphere. And here we have this orientation, this orientation. I can glue these together, and what I obtain is the following cylinder. A cylinder with orientation on the boundaries as follows. So this is eta, this is the metric, and it is non-degenerate. It is clearly non-degenerate. Non-degenerate because I can take exactly the same cylinder, but with opposite orientations on the boundary. In particular, I can take these boundary orientations, so exactly the opposite. And let me call eta inverse the form attached to this pair. Well, by using the factorization axiom, I can show that eta tilde is actually the inverse of eta. So we have that eta tilde equals eta inverse. Why? Because I can attach, I can glue this pair. So this is eta. This is eta tilde. I can glue, I use the factorization axiom. This is equal to what? This is, I obtain the cylinder with these orientations. But by normalization axiom, the linear form attached to this cylinder is the identity. So this completes the proof. Indeed, indeed, something stronger is true. Given a Frobenius algebra structure, I can always reconstruct the whole two-dimensional topological field theory. And I was particularly fond of giving you this example because actually this is an example which is very close to the way to which Dubrovin arrived to the notion of Frobenius manifolds. Dubrovin was studying the moduli spaces of topological field theories. At the end of the day, he was studying geometrical differential structure on this moduli space, and it was in this way that he arrived to the notion of Frobenius manifolds. So in particular, the idea, to be more precise, what is true is the following. Dubrovin was studying the moduli space of quantum field theory with extension n equal to 2, and he was studying the so-called TT star geometry. TT star geometry of his moduli space. Actually, he realized that behind this very rich differential geometrical structure, there was a deeper structure. That is what nowadays we call a Frobenius manifold structures. And roughly speaking, it is a family of Frobenius algebras. So what is, loosely speaking, what is a Frobenius manifold? Rather than to work with a single Frobenius algebra, now we will work with families of Frobenius algebras. This family will be parametrized by some base space. So we will have a base manifold for parameters of deformations, and over this base space we have Frobenius algebras. Actually, so the idea one should have is the following. You have a manifold, and over this manifold you have a Frobenius algebra. Actually, so the idea is the idea of a vector bundle. We have a vector bundle whose fibers are equipped with Frobenius algebra structure. But actually, this vector bundle will be identified with the tangent bundle of a manifold. Okay, so how much time still I have? Just to 25 minutes. Okay. Okay. So so I can now introduce a Frobenius manifold. Frobenius manifolds are objects which can be introduced in many categories. Can be introduced in the smooth category, in the real analytic category, complex analytic category, or formal category. Today, I will mainly focus on the complex analytic category. So, in what follows, M will be a complex manifold Tm and T star M will be holomorphic vector bundle. I mean, holomorphic tangent and cotangent bundle. And whenever I have a holomorphic vector bundle over M, I will denote by gamma MV the space of global sections. Or actually, well, yes, the space of global sections. Okay, so we have, as I here very vaguely said, we want to define a family of Frobenius algebras. So we need to define many gadgets. We need to define a product, we need to define a metric, and these must be compatible, non-degenerate, and so on. So now I will introduce many gadgets which are just the same as the previous one, but now in this differential geometric context. So a Dubrovin-Frobenius manifold, I use the name Dubrovin-Frobenius manifold, well, first of all, in honor to my teacher, who sadly passed away 2 years ago, and who was the leader in this research area. He was the one who introduced this notion. But I want to use this name, Dubrovin-Frobenius manifolds, exactly in this category, the complex analytic category, because this is the kind of object that actually he studied and which will be, by the way, the main focus of this course. So a Dubrovin-Frobenius structure on M, whose dimension is n, is the datum of, so we have many gadgets. First of all, we need a metric. So a symmetric, non-degenerate OM bilinear form eta so it is in the symmetric a section of a second symmetric power of a cotangent bundle, the metric. It is not a Riemannian metric. It is bilinear with respect to the holomorphic functions. So it is not an Hermitian metric, so to say. And we require that its Levi-Civita connection is flat. After that, we need a product. The product is defined once we have defined the structural constants for the algebra. So we require the datum of a 1-to tensor C I require that this is a section of a tangent bundle tensor the symmetric square of a cotangent bundle because I want to define a commutative product such that the induced multiplication of vector fields defined by this identity, where x and y are vector fields, is associative Moreover, by using the metric, we can attach to this tensor C a completely covariant tensor inside T a priori inside a section of the tensor product of a cotangent bundle times the symmetric power, the symmetric square of a cotangent bundle. So in other words, I am doing what physicists say to lower an index of this tensor. So I will denote this operation by bemol, just to recall me a musical isomorphism. I denote that I am lowering an index of this tensor. And a priori, as I said, it is just a section of T star tensor symmetric square of T star. But I require that it actually is in the symmetric cube of T star. So I require completely symmetry. And moreover, I also require that its covariant derivative with respect to the Levi-Civita connection of eta is in the fourth symmetric power of the cotangent bundle. Moreover, I also need, well, what we need? We need a unit for the product, and this is done here. So we have a vector field E, section of a tangent bundle called the unity vector field, such that the bundle isomorphism given by C blank E blank, this is a morphism of a tangent bundle to itself, is the identity morphism moreover, we require that such a vector field E is flat with respect to the Levi-Civita connection of eta. So we would have everything. Or we have a metric, we have a product, which is required to be associative, commutative, with some more requirements. Actually, inside this requirement of symmetry, there is the compatibility with the metric. And we also have a vector field E, which is the unity vector field, but for a Dubrovin-Frobenius manifold structure, we actually need to require a gadget more, an extra gadget, which is a second distinguished vector field, which will play an important role in the theory. And this is the Euler vector field. A second distinguished vector field, capital E, section of a tangent bundle, Euler vector field, which is assumed to behave particularly well with both the metric and the product. In particular, we require the Euler vector field to be a Killing conformal vector field, and moreover, we require that its flow preserve the structural constants of the Frobenius algebras. So we require that the Lie derivative of a metric eta along E equals a constant that I will set to be 2 minus t times eta. T is a complex number that will be called the charge of a Frobenius manifold, of a Dubrovin-Frobenius manifold. And as I said, the flow of E of the Euler vector field preserves the structural constants of the Frobenius algebras. Okay, this is the definition. It is a very rich structure with many gadgets, and it takes a bit of time to learn how to handle all this data. We have a metric, this tensor C, which is a tensor of structural constants, and two distinguished vector fields. One is a flat vector field, the unit for these products, and this mysterious, for the moment, mysterious Euler vector field. Let me do some general remarks, comments, or direct consequences of these definitions. So general remarks. So first remark, nabla, the Levi-Civita connection, is assumed to be flat. Hence, locally, there exists system of coordinates that I will denote by T1, Tn, in which, with respect to which, the metric eta is constant and the Christoffel symbols vanish. Second remark. From the fact that the Euler vector field is a Killing conformal vector field, and the fact that nabla is flat, one can prove that these two conditions implies that the Euler vector field is an affine vector field, that is nabla of E is 0. So that in flat coordinates T, the Euler vector field, we have the following form. We will have a linear expression. We will have a linear expression where Q alpha and R alpha are complex numbers. And, well, moreover, without a loss of generality up to an affine change of flat coordinates, we will always assume that, so up to an affine change of coordinates, we can assume that the first flat coordinate, T1, is always chosen so that the corresponding coordinate vector field equals the unit vector field. And moreover, the coordinates can be chosen so that the constant term in this linear expression R alpha is different from 0 only if this term, we don't have this term, that is if Q alpha equals 1. Fourth remarks, if we set okay, we can set eta alpha beta to be the pairing of two coordinates vector fields with respect to these flat coordinates, d over dt alpha and d over dt beta. And I can also set C alpha beta gamma to be C, the tensor of the second point of the definition, to be the evaluation of this tensor in this triple. In other words, eta alpha beta, C alpha beta gamma are just the components for this tensor in this flat system of coordinates. And what is the meaning of condition of these conditions? Well, the meaning is the following: is that I can I can lower the index of this in this tensor, and I can introduce C alpha beta gamma, and the first requirement C bemol is a section of is that this is required to be completely symmetric in alpha beta and gamma, so completely symmetric. But also we have this fourth requirement: the covariant derivative of C bemol must be completely symmetric. So let me erase here. So we also have this requirement that this object is completely symmetric in the four indices. But this complete symmetry implies the local existence of a function f such that C alpha, beta, and gamma equals the third derivatives of this function f. And if now you want to write down the associative, you can, for example, use this function called potential or prepotential of a Frobenius manifold in order to rephrase the associativity condition. And the associativity condition in terms of this potential function becomes the following: over-determinate system of nonlinear PDEs I will use the Einstein rule of summation over repeated indices, and I will denote by upper eta, gamma, delta with upper indices the inverse of eta of a metric. These are standard notation in differential geometry. So the equation of associativity are the following. So in this side we have alpha. Look at the indices: alpha, beta, gamma, delta, lambda, mu. In this side we have replaced alpha with the last one and the last one with the first one. So we just change the first and the last index. These equations are called Witten digraph Verlinde equations, associativity equations, shortly WDB Equations, and these are equations which rule the whole geometry of Frobenius manifolds. If you have in your hand a solution of these equations, you are able to reconstruct a Frobenius manifold structure on this manifold using the formula I gave before. And in particular, this formula, and also another remarkable formula, which is the following: eta alpha beta equals again a third derivative, but in which we have a first index equal to 1. And let me simply say, and moreover, finally, so this identity and also another identity. The Euler field rescales these potential functions up to quadratic terms in the flat coordinates. So, Frobenius manifolds are objects which are ruled by solutions of these equations. And as I said, one can introduce Frobenius manifolds in many categories, But these equations are a key point of the theory. For example, if you want to introduce Frobenius manifolds in a formal category, what you have to do is to start with the formal solutions of this system of equations. So I think that for today is enough. Next time, I want to give you some important examples of Frobenius manifolds. Examples that will generalize, in some sense, two examples at the end of the day, which will generalize two of the examples I gave to you this morning.